Here I have question 1. It says this question is about the motion of a charged particle in a magnetic field. A charged particle is projected from a point x with speed v at right angles to a uniform magnetic field. The magnetic field is directed out of the plane of the page. The particle moves along a circle of radius r and center c as shown in the diagram. Okay, so here we've got circular motion of this charged particle. Looking at A, on the diagram above, draw arrows to represent the magnetic force on the particle at position X and position Y. Now when we have circular motion, remember we have this formula over here that the force is equal to mv squared over r. And this is our centripetal force. This force is always inwards towards the center. So we would have our force, our magnetic force would be like that, always towards the center, causing that change in direction. Now we're looking at B. 1. The charge is positive or negative. Okay, so I have my magnetic field is coming out of the board. So we got something like that. Now, using the right hand rule for this, where the fingers point in the direction of the magnetic field and your palm is in the direction of the force, when we do that, we see that the current should be going down in that direction there. That would be our current. Now, the current is always a positive charge. So therefore, since we are going in this direction, this must be a negative charge. This must be an electron. So this is negative. And you need to put in there, if you put these points into your diagram, and then just say by the right hand rule. Then it says work is done by the magnetic force. Now remember, the formula for work is equal to Fs cos of theta, where F is the force and S is the displacement in the direction of the force. So because your particle is moving that way, your force is actually at 90 degrees to the direction. So the cos of 90 degrees is equal to 0, so the work done is equal to 0 joules. So whenever you have centripetal force causing circular motion, the force that is at 90 degrees causing that circular motion is doing no work. It then says a second identical charged particle is projected at position X with the speed v over 2 in the direction opposite to that of the first particle. On the diagram, draw the path followed by this particle. Okay, so I think I'll get rid of all of this writing. We'll start again. So we've got here a particle coming down like this, but now it's going at v over 2. Now, obviously, because it's going the other direction, the force will be in the other direction. You can use your right-hand rule in this. Your current will now be in this direction because this is a negative charge, remember, so this will be your current. So if you use the right-hand rule, you've got your fingers in the direction of the magnetic field out of the board. You've got your current up, and you'll see that you're going to have a force on this particle. It's going to be in this way. But what about the radius? Well, there's two things to think about. Firstly, you have the force. Now, because you've got everything is the same, that's the same, that's the same, this is the same, but your v is a half, you see that your force will now be F over 2. You'll have half the force. Your formula for circular motion, force is equal to mv squared over r. Therefore, your r is equal to v squared over the force. Now if I put in my new values here, I'm going to have we're now going to have v over 2 squared because you've got half the velocity and your force is a half. So this will become v over 2, that's a quarter, and then when you divide by a half, you're actually going to get a half mv squared over your force. So it's actually going to be half the radius. So you're going to get something like that, where the center of this is r over 2, and it will go in that direction like that.